Alright folks, Hannah is sick today, so I am recording my lecture so that Mr. Bunker does not have to do it. I want you guys to do 8.1 and 8.2 section reviews in class. Do it after I've concluded the lecture. We'll go over 8.3 possibly with the sheets tomorrow, or I may record another lecture for that. So 8.3 is on page 230 of your books. Aaron, you may need to pause the video at this point because I'm quite sure that they're all going to go run to their crates or pull it out of their bags at this point. Okay, so 8.3 is bonding theories. We talked a lot about molecular orbitals when we did the Aufbau diagrams. If you'll remember, the first level was S, the second level was P, the third level was D, and the fourth level was F. What we didn't cover was that they aren't always exactly that way, that there really are a combination of orbitals when you bond molecularly. So when you add H2O, for instance, when you're doing water, those orbitals are not going to look the same as they did just for the atom. So there are some pictures at the bottom of page 230. Notice where the nuclei are in comparison to the outer bounds of the electron cloud. Notice that the electrons probably spend most of their time between the two nucleuses. They don't get out a lot because those are the places where they're going to be most stable, at least in the s orbital. Now, when you look at the p orbital on page 231, notice that the plus sign always represents the nucleus, and notice how when it's simply a p orbital by itself that the nucleus is in the middle and the electron cloud can extend to either side. Now, when a p orbital bonds with a p orbital, notice how the electron shell shifts its probability. The probability now increases between the two nuclei as opposed to being outside. Notice there's a smaller probability of it being outside the nucleus. I will let you look. Notice all these bonds have a name. I'm not going to require these names. I want you to be aware that all of these bonds have a name. Then if you turn the page, on page 232, it covers the VSEPR theory. This is just a very fancy way of saying that atoms, when they bond with others in molecules, are going to have a specific structure that allows the electrons to be to let these bonded atoms be as far away from each other as possible, yet still be part of the same molecule. And when that happens, you end up setting up geometric shapes. Notice in methane on the bottom of page 232 that it forms this tetrahedral shape where it's almost like a pyramid, where the where the hydrogen atoms are the three corners of the bottom of the pyramid structure and also the top point, whereas the hydrogen is in the middle. And so notice that the hydrogen is what sets the distances between, because it is that bonding, it is the carbon that sets the orbital distances between the two, because remember, the carbon can bond 4 times, and so it is setting the angle to which the hydrogens want to be together, because the hydrogens naturally in this case are going to repel each other because their positive nucleuses are not going to want to be together. Remember, opposites attract, likes repel. And so these hydrogens are going to try to get as far away from each other as possible. Well, there's 4 of them. And so you're going to set up an optimum angle to where they can be as far away from each other as possible, yet still be part of methane. The same is true of ammonia. So, but notice too, remember we talked about ammonia had that unshared electron pair. Notice for ammonia that is the top of that pyramid, which is why ammonia tends not to stay ammonia. It has a tendency to bond with other things. So, there is a whole list of atomic shapes. There's linear, there's triagonal, there's triatomic, pyramidal, tetrahedral. You get the picture. I just want you guys to be aware. Remember, we talked about how what I draw on the board is 2-dimensional, but atoms operate in a 3-dimensional space. So, what this allows us to do for the VSEPR, if we go back to the hybridization of the orbitals, where instead of just having a straight s orbital, you might have an sp orbital where they have combined. This helps us to accommodate some of those shapes. And so On page 234, notice they have a VSEPR configuration, but they've illustrated what the S and P orbitals look like and how that they really are still there, but it's all part of a larger shape for the molecule itself. We covered double bonds. This is also true for double bonds. If you notice the ethene molecule on page 235, they have a molecular representation. Notice the pi bond. That's a little odd. Read about the pi bond back on page 231. And notice how that this is one of those places where the electron isn't so much running around the atom like this. It's mainly has picked a side, either this side or this side. There's not going to be a lot of crossing between the two. The areas of probability are on either side. So notice in the ethene molecule that is that other bond that is represented. You have your traditional bonds, but then you have this pi bond, okay? And then notice too the ethene, EHTYNE, on page 235. It has another way, and it shows you how all of these things got added together in order to create this big molecule and all of its probabilities of where its electrons are. So I also want you to remember this has to do with its handedness, especially the pi bond. That kind of lets you know if you have a left-handed or a right-handed molecule. So that's all I had for 8.3 for now. I just wanted to introduce the concept. I want you guys to do the 8.1, 8.2 section reviews for Mr. Bunker, and then we will go over 8.3 in more detail and work through some problems maybe tomorrow. So thank you very much. We will talk to you later.